The James Webb Space Telescope has captured something truly unusual: a powerful and sudden burst of energy erupting from Proxima Centauri, the closest known star to our solar system. This event, as mysterious as it is powerful, has stunned astronomers and added a new level of complexity to our understanding of stellar activity. Proxima Centauri, a red dwarf located just over 4.2 light-years from Earth, is already known for its erratic and turbulent nature. But the scale and characteristics of this latest flare far exceeded existing scientific expectations. Before we begin, don't forget to like and subscribe to the channel so you don't miss out on exclusive news. The discovery was made as part of an ongoing survey of nearby star systems by the James Webb Telescope, which is studying potentially habitable exoplanets and the dynamics of their host stars. Proxima Centauri is particularly interesting because it has at least two known planets: Proxima b, located in the star's habitable zone, and Proxima c, the larger and colder planet located further out. However, the observed flash was so powerful that it momentarily overloaded several of the telescope's instruments, recording a sharp spike in both the optical and infrared ranges. This was not just another stellar flare. It was a colossal burst of energy that lasted only a few minutes, but left such a strong trace that data analysis continued for weeks. Proxima Centauri has long attracted attention due to its proximity and the tantalizing possibility that Proxima b may have conditions suitable for life. However, its reputation as a flare star, prone to unpredictable and sometimes destructive eruptions, complicates the picture. The James Webb Telescope's discovery raises important questions for scientists. What caused such a bright flash? Was it a superflare, orders of magnitude more powerful than any previously recorded from this star? Or is this a hint of a new type of stellar activity not previously observed in red dwarfs? The flare was not just powerful, it had an unusual spectral signature. Analysis of the data revealed a complex combination of ultraviolet and infrared radiation, interspersed with sequences of energy patterns that do not fit known models of stellar flares. Usually, flares in red dwarfs are caused by the restructuring of magnetic fields in the star's atmosphere, similar to solar flares on our Sun. But this event included not only thermal radiation, but also non-thermal emissions, indicating the acceleration of particles to nearly relativistic speeds. The telescope's instruments detected traces of charged particles moving through the stellar wind, colliding with nearby matter and generating bursts of synchrotron radiation, a hallmark of extremely high-energy processes. Even more intriguing is the timing and direction of the flare. It was directed almost like a narrow beam and, accidentally or intentionally, toward the inner planetary zone. If Proxima b was in a certain phase of its orbit at that moment, it could have been directly exposed to the full power of the flare. This has serious implications for its atmosphere, magnetic field, and potential biosignatures. A flare of this magnitude could blow away a significant portion of the atmosphere if the magnetic field is weak or absent. Or it could trigger complex photochemical reactions that create temporary biomarkers, making it difficult to distinguish between the planet's natural chemistry and signals generated by life. The intensity of the flare, measured by the telescope's near-infrared spectrometer, was equivalent to tens of thousands of the largest solar flares observed in our system. For a star that is only a fraction of the size of the Sun, this is a colossal amount of energy. The emission lasted less than 3 minutes, followed by a longer tail of gradually fading radiation. Ground-based observatories were immediately alerted, triggering a wave of follow-up observations in different wavelengths. But none of them could match the accuracy and clarity of the data from the James Webb Telescope. Its location at Lagrange point L2, free from Earth's atmospheric interference, allowed it to see details invisible from the surface of the planet. This flash raises the question of the habitability of planets around red dwarfs. These stars make up almost 75% of all stars in the Milky Way, and many of them have exoplanets in narrow habitable zones. But if such flares occur frequently, or even rarely, But with such intensity, they could seriously hamper the development of life, especially in the early stages of a planet's formation. The young Proxima b, which has been subjected to repeated bursts of radiation, may have lost water or failed to maintain the molecular stability necessary for organic life. Even today, any microbial life there would likely have to be found beneath the surface or in layers of rock to avoid DNA damage from ionizing radiation. There is another intriguing aspect. The data suggest that the flare may not have been an isolated event, but part of a longer-term cyclical buildup of magnetic tension in Proxima Centauri's core. Instruments recorded subtle changes in the star's brightness and radiation spectrum in the days leading up to the flare. These precursors are almost imperceptible, but they hint at the possibility of creating an early warning system, subtle energy fluctuations that precede more powerful emissions. If such a model can be developed, it will revolutionize the study of weather on stars and allow us to assess the radiation environment of exoplanets in real time. Astronomers are particularly interested in the possibility that the flare could have caused secondary effects in the vicinity of the star. The space around Proxima Centauri is not empty. There is dust, gas, and possibly small comet-like bodies in a sparse debris disk. High-energy radiation could have triggered a cascade of photon interactions, creating temporary shock waves or ionization fronts. Such phenomena can affect not only the orbits of planets, but also the quality of observations of the system from afar. Understanding these processes will help refine methods for searching for biosignatures in the atmospheres of exoplanets. The flare also led to a reassessment of Proxima b's magnetic field. Earth's magnetosphere protects life from solar flares, but the strength and structure of Proxima b's magnetic field remain unknown. If it is as powerful or stronger than Earth's, it could protect the atmosphere even during powerful flares. If not, the consequences could be catastrophic. Frequent radiation shocks would destroy the atmosphere and sterilize the surface. Future observations by the James Webb Telescope may indirectly reveal this by analyzing spectroscopic signs of ionospheric losses or changes in the planet's albedo after flares. The detail of Webb's data allows us to reconstruct the evolution of the flare in near real time. In the first moments, a sharp increase in ultraviolet radiation was observed, followed almost immediately by bursts in the near-infrared and X-ray ranges. Each stage reveals different layers of the atmosphere and the structure of the star's magnetic field. The models currently being developed seek to understand the interaction between convective zones, magnetic loops, and plasma ejections that lead to such colossal energy releases. It is a kind of forensic analysis of stellar violence that is changing our understanding of the life cycles of low-mass stars. This discovery may also be important for the search for technosignatures. Any intelligent civilization on Proxima b would surely notice such a flare, and it would be an important moment in the history of their planet. On the other hand, if other civilizations are observing Earth-like planets, such giant flares could either disrupt the biosphere or prompt the development of protective technologies. Understanding the frequency and scale of such events could help future SETI projects, including the selection of search directions and the interpretation of energy patterns that may indicate the activities of advanced civilizations to mitigate stellar threats. In a broader astrophysical context, this flare fits into the study of magnetic reconnection, a mechanism underlying many explosive cosmic phenomena, from solar flares to gamma-ray bursts. The ability to observe a high-energy burst in real time at such a close distance provides scientists with a unique laboratory for testing theoretical models. Magnetic reconnection remains one of the least understood processes in astrophysics, especially on scales large enough to affect planetary systems, but large enough to change the behavior of the star itself. Data from the Webb telescope may finally fill this gap by showing how magnetic lines break, reconfigure, and release energy at nearly the speed of light. Even how the flare affected the telescope's sensors is helping to improve future observations. The bright flash caused a brief saturation of some detectors, And now, the calibration team is studying how to adjust exposure settings for unpredictable high-energy events. This feedback loop between discovery and engineering improvements highlights the dynamic nature of space science. Each unexpected observation by Webb not only expands our theoretical understanding, but also improves the telescope's readiness for new surprises. If you enjoyed this video, please like and subscribe to our channel. Also, let us know in the comments what you think about the giant flash from Proxima Centauri. Is it a signal from aliens or a natural phenomenon? We value your opinion. Thank you for watching, and we look forward to seeing you next time.